came to fruition.
All right, today we have Professor Bob Bing giving a CITA seminar, and Doug got his PhD from Cambridge in UK in 1976, and that's a long time ago. 1979, since then he has been a faculty at UC Santa Cruz, and Doug has a long list of awards, but I'm not going to tell them here. Doug is the founding director of the Cavity Institute for Astronomy and Astrophysics at Peking University, where I got my undergraduate degree from 2007 to 2012.
This is an honor.
Actually, Doug has very strong ties to Canada, and Doug got his undergraduate from McGill's University. And his father actually helped in establishing the diplomatic relations between Canada and China in the late 1970s. Right? And Doug is best known for his work on planet formation and evolution, but he has lots of ideas on very different topics. And he used to have an army of undergraduate students working on very different topics, and I was one of them. You can see a long list of graduate students or undergraduate students here. And today, Doug is going to tell us about applying planet formation to the formation of gravitational wave sources.
Thank you.
You have 15 minutes.
Okay, thank you. Okay, so the color code is these are blue is undergraduate, green is graduate student, and orange or red is postdoc, including a super postdoc, and black is senior collaborators. So, it's my pleasure to be here, and I was one of the first visitors to CITA, in 1985. So I'm going to talk about a whole bunch of seemingly unrelated topics, but I hope by the end of this hour, I would convince you that there is a coherent theme, that galactic nuclei is just a macrocosm, not macrocosm, of planetary systems. And so here are some questions you may like to ask. What causes the emergence of a disk of young stars around the galactic center? This is a very exciting subject. People are seeing proper motions around there, and why are the high-redshift quasars so metal-rich? A problem that Pavel got me start to think. And can stellar remnants power X-ray energy flux from AGNs? And can dynamical evolution of nuclear clusters be affected by gaseous and stellar disks? Can AGM become, how do AGMs become inactive? And finally, there's this link. Can a fraction of the gravitational wave events be due to stellar black hole mergers around AGNs? Okay, so there's a wide range of topics, and how do they all link up together? So since the late 60s, it was first discovered these quasars, and then very shortly after, and my mentor, Lyndon Bell, and proposed this idea of an accretion disk around massive black holes. Today, the evidence of massive black holes is well established by observations such as NGC 1275, and where there's a major source, and you can see the Keplerian orbits around the central engine. And it was all because of this initial theoretical work. It initiated folks to develop so-called accretion disk models, and from there, people try to build and what is called the unified model for active galactic nuclei. In addition to gas, we also see star clusters near these massive black holes. The most famous one that's close to home is the one around Sag A stars. And in the center of our galaxy, there's these these massive young stars that moves around with a proper motion, and they form almost two populations. One population essentially resides in a disk-like configuration. They are a little bit older. They're called disk stars. Another group of stars are the ones that you can really see proper motion nicely is in the central region, and they're called S stars. And they have a slightly different age. So I'm going to start this talk with the three, I believe, the three widely accepted assumptions. That there is a massive black hole in every galaxy. And today there's been a lot of observations on surveys of galaxies, and they turn up evidence, and they even find correlations between galaxy properties and massive black holes mass. And so that, I think, is probably controversial. And the second issue is around each massive black hole, there's usually a nuclear cluster. And some of the time we can see it, some of the time we can't. The time we can't is because the central engine is, outshines the star cluster around it. And, but in the case of the galactic center, this is a good example. Three, that AGN, so-called active galactic nuclei, occurs when the massive black hole is fed by a disk. And this is Lynden-Bell's original concept, and that today I think is generally accepted as a working model. Based on these three well-accepted proposition, and we think it is relevant to ask the question, what happens during the active phase when you have a disk and when these stars from nuclear cluster go through the disk? Okay, so we have examples where companions can go through the disk, and this is an example not quite on the galactic scale, but something that is on a protostellar disk scale, where people actually see the appearance of shadows which evolve in time. These shadows move around, and one possible interpretation is that these shadows are the shadow casted by an embedded planet as it goes up and down in some way, and so it perturbs the disk structure and to cast a shadow of this kind. And and we think this is a general phenomenon. So since I'm making this analogy between protostellar disks and AGN disks, let me convince you there is really close connection. Okay, if we look at planetary systems, the mass ratio between the planets and the whole star is typically in this range of 10 to the minus 6 to 10 to the minus 3. And if we look at the galactic center, and when we look at the star mass and or companion mass between there and the center region is somewhere in a similar range. The period of the planets in the solar system range from months to centuries, and whereas the period of these galactic center stars, the fact that we can see their proper motion in an astronomer's career tells you it ranges from years and perhaps to millenniums. And no one has lived that long yet. And then the radius to semi-major axis ratio for the terrestrial planets, and even including the gas giants, is typically 10 to the minus 4. Likewise, the radius to semi-major axis ratio in the galactic center for these stars is about 10 to the minus 5. So we're in the same ballpark. Now, when we look at protostellar disks, and in comparison with AGN and young stellar disks, and if we look at their mass, the disk mass to central mass is typically in this range of a few percent. Likewise, in typical AGN disk, as I will show you later, and it's also in this range of a few percent. And the aspect ratio is of order a few percent, and the aspect ratio of AGN disk is also of order a few percent. The gravitational stability parameter some refer to as 10 raised Q, is typically of greater than 10, and in this system is of order 1. And the persistent time scale of protostellar disk is of order a few million years, and the persistent time scale of AGN active phase is of order from 1 to 100 million years. So, so there are considerable amount of similarities. Of course, the mass of the central object itself is much larger, and relativity may play an important role in this area. But the important thing are these ratios. Okay. So if we want to study this effect of star going through the disk, we need to know something about the nuclear cluster property, and we need to know something about the accretion disks. And I will go through this to give you some kind of almost semi-analytical, semi-empirical type of construct here, because the theoretical construct here involves a lot of uncertainty, and I'm going to introduce some of these constructs. So the first thing to do is to construct something about the accretion disk. And how do we construct accretion disk? Typically, when we look at AGN disk, we think of two parameters. One parameter is the so-called efficiency factor, and this is to link how much of the rest mass energy gets converted into luminosity. The other is the so-called Eddington factor. This is what is the accretion rate relative to this Eddington factor. To determine that, we turn to statistical analysis based on a Sloan digital survey, and where they pick up a large population of AGNs, and with their luminosity function, we can start to look at their evolution in the redshift. And this general evolution in the redshift tells you that as you go forward in time, and gradually the luminosity function start to evolve, and this can be interpreted as having a black hole that's fed at some accretion rate, and that is a function of the mass of the black hole, and so on and so forth. So this has been done over the last 20 years by various people, and including those who are into X-ray astronomy as well as in theory, and so on and so forth. So what they find is that the Eddington factor is in this range of 0.6, around there, plus minus. There's a large degree of uncertainty, and this efficiency factor is somewhere slightly less than 0.1. From a theoretical point of view, this is all relatively reasonable, but this is an observational constraint that one can make. So, and then you can work out time scales, and you can work out various other things. So now, what does this mean? Okay, so if I now start to go back to the standard heuristic accretion disk model, which basically tells you something about the accretion rate is regulated by the viscous transport of angular momentum. And if we try to parameterize them in some way with this very ad hoc prescription and do it in terms of alpha, then you can write down all of the m dots and quantities. You can scale it in terms of the critical surface density for gravitational instability, and divide by the stability parameter, and you can work out things like this effective viscosity in the form of an aspect ratio. So there are three unknowns: alpha, aspect ratio, and Q. But from the previous determination of the Eddington factor and efficiency factor, one can work out a relationship just based on this kind of steady state accretion disk model in terms of these, what we would call ignorant parameters. Okay, alpha is certainly something that is a holy grail of theoretical astrophysics, and we don't know that very well. And but now aspect ratio, again, is somewhat determined by the physics of the disk and its Q value. But there's one relationship that will already tell you immediately from just the fact that we know the Eddington factor and the efficiency factor. There is one relationship that links 3 parameters. So we need two more constraints to do that. Once again, I appeal to observation, okay, and partially observation, partially theory. And partial observation that you can work out is use the reverberation map. And there you see with some time delay in the flare, the variation of luminosity at various locations, we can work out both the temperature and the aspect ratio as a function of radius. And then we can look at this possibility using theoretical consideration that if the disk is almost self-gravitating, maybe then spiral density wave will come in to provide a torque, a gravitational torque, to transport angular momentum from one location to another. And you can link that. If the Q value is very large, you go back to the standard low alpha, or if it's very close to 1, you can get into this state. A lot of this work has been done by various people who had associated with CITA. So we have 3 parameters, 3 relationships, and then therefore we can determine from there, we can construct a Q and alpha and H that can account for all of these things. Okay, so then one can also work out from here the value of optical depth and in the disk, and you'll find that the disk within about a few parsecs is very optically thick, so these type of gravitational instability will not lead to fragmentation. Okay, so now the next step was done 25 years ago, and by Pavel, and who look at this question that if you have an intruding star that goes through a disk for this given aspect ratio, given surface density, and what would be the drag on this? Okay, so there are 2 parts. One part is from hydrodynamic drag, the other is from a density wave that is excited. So you can describe this all in terms of a drag coefficient, and that links up the possibility either in the hard and the soft limit, which means whether they're moving so fast the relative velocity is small or large compared to the surface escape velocity of the star. Okay, so you can get into this kind of capture, and in fact these captures can be actually even larger if that interaction can inflate the radius of the star. But let's start without inflation. You can get this type of parameter.
So
now,
the dominant effect is the gravity, so what does it matter if you inflate the star?
Because the cross-section, you can have both the soft and hard limit. And if you get it to be very big, then you get into the hard limit in the sense that there's, it's your geometric cross-section becomes more important in terms of what you encounter as a drag.
That means that you hit the disk with a velocity that's larger than the escape velocity.
The escape velocity is a function of the size of the star, right? If the star inflates, it will be, yeah, okay. So you can have these 2 limits, okay? And so then you can ask the question, under what condition that you go through this drag, that you will settle down into a disk with certain thickness, and that gives you a critical condition. And then Pavel put together this link with phase space distribution, and as obtained from Lee and Goodman. And then to work out, from here, you can work out the part of the phase space you can actually cause stars to be trapped into the disk. And today, of course, we can use some guidance on here, especially with this normalization coefficient, because there have been a lot of observations of nuclear clusters. And if we use the nuclear cluster information from these regions, especially in the Virgo cluster, and you can actually derive a rate, and you can work out the trapping. So this tells you the fraction of stars that can get trapped, and then with the normalization, you can get a trapping rate. Okay, so these are applications of things like various surveys of nuclear clusters, and by looking at their half-mass, half-light radius, and looking at their surface brightness, and we can determine these normalization factor, and we can apply into this equation, and we can work out the trapping rate. There's some average trapping rate, and that trapping rate, you can relate it to all of the different relationship here in terms of the aspect ratio, the Q value, and all the rest of it. You put it into the disk model, and you link up with what we know about the host galaxy. And first you link up with the mass of the black hole, and then the mass of the black hole can be linked to the property of host galaxy using M-sigma relationship, and you can get into a quantity that tells you the trapping rate. Okay, once it's trapped, what happens? Okay, once it's trapped, it gets into this disk, and you can calculate the boundary accretion rate. And this accretion rate is very fast, despite the fact that the disk has a temperature in excess of 10 to the 4 degrees. And the reason for that is because the density here is more than 6 orders of magnitude larger than the densest core of molecular cloud cores. Okay, and so the boundary accretion rate is exceedingly fast, and they can actually double their mass in time scale that's short compared to 1 million years, and this is the formula, and there's a runaway accretion. Yes?
Just a couple quick questions. About these spiral density waves
Yes.
stirring things up,
Yes.
what does one really mean by trapping in that context?
Usually these objects are very small, so their influence on the disk is not too strong.
Well, I understand, but I was thinking more of the influence of the spiral density waves on these small objects.
Right. So what I mean by trapping is that they get within one density scale height. So the density is more or less constant. It is, that the density in that part of the disk is relatively high.
And then I see here you could argue that they can accrete in spite of having very strong winds or radiated.
Just wait for a minute. Okay, I'll come to that. Okay, so this is without feedback. Okay, so if you have no feedback and you can form stars very quickly, how big can you do? You can make it so big that it can accrete until its lifespan is matched, and that would give you a mass of 600 solar masses. And of course, this will not happen because there may be stellar wind. So if I now put in a formula for Wolf-Rayet type of wind or AGB wind, and then there's a self-limiting factor because these wind intensity is related to parameters that we know, such as the mass of the star. So,
momentum flux is at most of order
but not in the Wolf-Rayet stage. Okay, so it's dominated primarily by Wolf-Rayet star. Okay, because these are massive. So and then you can work out from that self-limiting factor, something is in this range or in excess of 100 solar mass, depending on where you are. Okay. Now, so by the way, this whole process will tell you that there is wind that's ejecting and there's gas that's being accreted. So it is, when I get this mass, it's a balance between these wind and the accretion. Okay, and so that gives you an equilibrium. If the mass is small, then the wind is not so intense, and then you accrete more. If you accrete too much, and then the wind becomes very intense, you get regulated. The actual process itself is still under investigation. We're trying to look at this process. It's very much like Jupiter formation, as some of you have looked at this accretion process. I now come to that in a minute. One other thing that is very interesting, and I'm looking at with Matteo Cantillo, is how it refreshes the envelope. Okay, so the Wolf-Rayet is not like an isolated Wolf-Rayet. It gets recycled and it gets reprocessed. So because it's being accreting. It's accreting at the same time as it loses.
But why does it lose the hydrogen? In Wolf-Rayet star has no hydrogen anymore.
Yes, because the material that you accrete in carries some hydrogen, and then it loses, it processed in there, and it gets returned back into the reservoir. And this whole process is cycling. Okay? It's got refreshment. And this is put it into the Mesa code, and we're trying to look at some aspect of this. Okay. So the first thing you see is that these stars can maintain to be very big, and they can produce supernova, they can produce black holes. And this is not like normal supernova, because the normal supernova in isolated environment, if they start with 100 solar mass, they'll lose more than half of it before they go off the main sequence. And here, you're maintaining at relatively high mass, okay? And then further out, the accretion rate is lower, the equilibrium mass is slightly smaller, and you tend to produce neutron star and white dwarf. And all of this material will pollute. And around AGN disks, and especially around 10 to the 8 solar mass black hole, and this material that comes out of this disk in this high density environment, they never escape. They're retained in the local region. They pollute this local region. And furthermore, the supernova remnants get shared out very quickly, because the Keplerian velocity here is over 1,000 kilometers per second, and they get shared out very quickly. So what does this mean? Okay, so if we now look at the remnants of this material, we make comparisons with the region around the black hole. There's broad line region and narrow line region. The broad line region is generally associated with a disk. And when we look at the broad line region, you notice right away, okay, that there is, these are early studies, and I'll show you a study that was done last year. And the study already show you that there's supersolar metallicity around these AGNs, and which is independent of redshift. Okay? So if you generate these in this neighborhood, and you would have thought the heavy elements would accumulate, you get dirtier and dirtier, and you should have higher and higher metallicity. No, is essentially independent of redshift. And if you look at the narrow line region further out, you find they're subsolar. And if you're still further out into the region in the halo region of the galaxy, they're very subsolar. So it tells you that the pollution occurs primarily in the vicinity of the broad line region, which is typically about a parsec or so. How does this pollution occur? I talked about supernova. I talked about these models of supernova that did not lose mass on the main sequence before they went off. And then you can work out their yield, and with a formula like this, and typically you can work out that rate. And we're talking about Wolf-Rayet winds, and as you said, that many of the winds product are heavy elements that return back to the system. So we can work out from here the metal production rate, here the metal production rate, and since we know the capture rate, we can work out the rate of heavy element generation in this local neighborhood. Of course, it won't stay in that local neighborhood, because the disk is evolving. As the disk evolves, not only angular momentum is being transported, but these contaminants would also get transported, and they would smear out. This is a bit like grains inside protostellar disks, and you can also evolve how their distribution will evolve in time. The reason they are redshift independent is because when the disk generates this heavy element, and there is accretion, and that keep on bringing this material, the byproduct of this stellar evolution, into the massive black hole, and you can then generate this kind of supersolar metallicity. And you can make a comparison. This is last year's model based on SDSS data by an undergraduate student from Beijing Normal University. And so here you can look at the different redshift. They fall more or less along the same correlation, but they have dependence on the mass of the black hole, and all of that can be reproduced. So we see the galactic center. We see this young generation star. This star could be produced from this type of disk trapping, but there's another group of stars which are not in the same plane, nor do they have the same age. How do you do that? Well, the disk is fed by the interstellar medium, which is turbulent, and this AGN disk could change in orientation, and when it does that, when it changes in orientation, you trap different group of stars, because the angular momentum vector of the disk can change in time, and what you're seeing is possibly trapped stars over different stages of this evolution. We see no disk today, but the fact that there are so many young stars, only a few million years old, it tells you that at some point there was a disk, and the orientation of this disk may have changed.
So you think that the stars that are in a disk are all there because it's still young, and then you have many other stars?
But the disk is gone.
Stars are all old.
Yeah, they were a little older. They're not very old. Okay, they're about 10 to the 8 years old, 10 to the 7 or 8 years old. The S stars. Yeah, they're older. They're different generation. Okay, so if this process is important, this process may actually tell you that you can never get to Bokal-Wolff distribution, stellar distribution. This is known, well known, that when people look at black holes, due to two-body relaxation and many other things, you should get a cuspy type of structure. And that is just from the stellar dynamics. But if you have gaseous disk comes in, and that preferentially take out some of these objects, and this will get modified. And likewise, this would also change the tidal disruption rate, because you have a tendency to really wipe out those when that is on nearly parabolic orbit to the center. What happened to the black hole remnants that is generated? Well, I talked about the gas that's returned. Let's talk about the black hole, the stellar black hole. That we talked a little bit about this before. And if you have a recoil velocity that's relatively small, and in comparison to the neutron stars, and you find that almost all of the black hole that even have a little bit of recoil, and they would still be nearly co-moving with the disk, and they will all be trapped. So the trapping rate of the original star is equivalent to the trapping rate of the black hole remnants that it produces. So you can work out this type of capture rate, and then once it's captured, it accretes again. And this time, it accretes at the Eddington limit, and because the amount of energy produced and becomes significantly larger than that you accrete onto the main sequence star. Yes?
So after these stars are trapped, are you assuming that they're liberated after the neutron star black hole is formed and they have to be retrapped in the disk?
Could you repeat that? I didn't quite get it.
Yeah, so why do these neutron stars and black holes have to be recaptured? Is the supernova...
Oh yeah, they just kick them out a little bit. Okay, so, and if they kick out too much, the gas density is low up there, and you want them to get back to the high density region, and you want them to move at the same velocity as you, so your gravitational cross-section is larger. Okay, so the kick gives you a little bit of perturbation, but it's not so little you get trapped again very quickly.
Isn't it a bit of a leap here to say, oh, gas goes in and it accretes? Because radiated feedback at a large radius from a black hole, for example, in principle limit its accretion.
Yeah, it could be. Right, but then that, yeah, and that effect is more associated with preheating and various other things, and that requires ionization. And this disk, entire disk, is already fully ionized. Okay, where in that region of the disk, in order for aspect ratio to be a few percent, you're moving around at Keplerian velocity over 1,000, your sound speed is got to be up enough, and you're already ionized. And so the only reason you can accrete like this is because the density is so high. Okay, so the preheating effect you refer to probably is not so important, but maybe there's a Bremsstrahlung effect that could play a role. Okay, it could be.
It sounds like there could be some solvers.
Yeah, right, okay, yes.
So since you're dealing with very massive stars, couldn't it be the case that you dominate by more exotic processes like parent stability or direct collapse?
There could be, yeah. And so I'm assuming that we didn't get there so highly, and this is something that Matteo is doing some computation at this moment. Okay, if it accretes too much, then we get into the standard gap formation type of process, and there are some feedback, and this has been looked at by many people, and including many in this room. So now, how does this black hole accrete? Now, the next point I'm going to make is no longer about the mass, but about the angular momentum, okay? Because when I talk eventually about gravitational wave sources, their spin is important. Okay, so we're now talking about what the black hole would accrete and how they would accrete in terms of angular momentum. So this is also very simple. And so now, there's two or three relevant radii. One is the Roche radii, the other is the boundary radius. Okay, if the object is very low in mass, okay, so then the Roche radius, okay, is actually inside the boundary radius. Okay, and if it's inside the boundary radius in this case, and then what happens is that when they cross over the Roche radius on its way, the boundary radius on its way to the Roche radius, it actually feels a tidal torque. So that torque makes this flow turn around to give you a prograde spin. And anybody who's done these type of simulation with an embedded planet, and they will see, oh, there's a prolate spin, even though if you just look at the simple gradient, it should give you a retrograde. And that is one limit. Another limit, okay, is this is actually a limit when the mass is small. The other one is when the mass is big. When the mass is very small, the boundary radius is actually inside the thickness and also inside the Roche radius. So after it flows through the Roche radius, on its way down to the boundary radius eventually gets accreted. By the time you reach the boundary radius, the torque from the host black hole is no longer felt. So when you accrete onto these objects, you conserve angular momentum, you get a retrograde spin. Okay? In reality, that the disk is quite turbulent, so the spin can go one way or the other. And
this is still the small black hole case.
yeah, you can look at two limits, one small, one large. Yeah, this has got to be the small one, right? So you can go either way, okay? I'll come back to this point later when I look at, gravitational waves. Okay, so at this rate we were looking at, so at any given time you can have 10 to the 4 of these objects present in an AGN disk around a black hole of 10 to the 8 solar masses during the active phase. So how do they interact with each other? They interact with each other just like planetesimals. Okay, you have similar number, you have gas. The gas damps down their eccentricity, and their eccentricity is excited by their mutual interaction. This is the time scale for eccentricity excitation. This is the time scale for type 1 damping. And if you link these two, you get an equilibrium eccentricity. And typically, the equilibrium eccentricity is so small that the excursion, the radial excursion, is actually small compared to the Roche radius. Yes?
Are there similar estimates for the inclination?
You can do the same, yeah. I'm focusing primarily on the eccentricity, okay? And so you can see that this is precisely the type of point that people talk about feeding zones. They talk about isolation mass. In order for there to be feeding zone and isolation mass, the relative perturbation between the objects has to be sufficiently small so they don't cross each other's orbit all the time. And so you can work out, based on planet formation ideas, and what is their isolation mass, what is the feeding zone. And you find that quite often, the isolation mass composed of several small black holes. Now, then what happens? Then the similarity breaks down. So whereas the planetesimals, when they capture into each other's Roche radius, the Roche radius is typically 100 times larger than their physical radius. So once they get captured, there's a good tendency for them to coalesce. But for black hole, there is 7 orders of magnitude to go, even before gravitational radiation becomes important. There is about, you can get down to about a few kilometer size, and starting from fraction of a parsec. So it's a long way to go, and they don't merge immediately. And so what happens is that they tend to capture each other. They tend to form small clusters. So here I have 10 C black holes here. They accrete gas, so their Roche radius start to increase. They start to see each other. They capture each other into binaries, sometimes exchange partners, and they form these little tight groups, but they don't coalesce yet because their separation physical radius is so small compared to their Roche radius. Yes?
So when they capture each other, these are individual binaries rotating each other. They're not captured into mean motion resonance.
No, they don't. Yeah. And you can also capture them from type 1 migration, something that is close to the heart of many, okay? And this type of process can give you several small clusters. Now, why is that important? When you form these binaries, when you first form these binaries, the binary interact with the disk here and here, and that will cause them to tighten. But this is not the dominant effect. This effect, you see, here is 1 parsec, and you get into a Roche lobe at 0.01 of a parsec, and using this interaction with the surrounding disk, you shrink by another factor of 10. Then the tide from this central massive black hole weakens. Okay, so you can't quite go all the way from here down to there. Yes?
Are these scales as viscosity negligible in these gaps? Or?
Well, you can, even with no gaps, you can still calculate the same thing. Okay, so you can calculate with gap or without gap. If it's with gap, then you only interact at a distance. But if you have large viscosity and or in the thermal limit, there's no gap, then they have a common envelope. Okay? And then the interaction is from the common envelope with a binary, not from the tides. So many people have made claims this is important. This is only important from here to here. And there are 8 orders of magnitude to go. Okay? So it's a long way to go. So how do we do it? Okay. This, if you didn't have, well, you're going to get a certain binary disk anyway, right? But then if you open up a gap, that certain binary disk is going to go away. gradually because there's no more supply. Okay, so if the binary becomes very, very small compared to the Roche radius of their combined Roche radius, they go way in the middle, and there's a certain binary disk on the outside, they can't take away so much angular momentum as such. There is a little bit of, you have to have a torque. Okay, you have to have a torque, and that torque, you remove a little bit of angular momentum from here and here. If it's not continually supplied, the rate of angular magnetic extraction is limited.
But it will be continuously supplied.
If you have a gap, then you won't. If you open up a clean gap, then there won't be. Okay? In this case, that's not the case. Okay? But if you open up a clean gap, then it wouldn't be. And because if you don't open up a clean gap, your mass will continually increase. You continually increase until you're more and more into the thermal limit. Then you get cleaner and cleaner gap. Okay.
I'm just curious, have you done the hydrodynamics for the binary capture?
Yes.
In a gravitationally active disk, one with
No.
density waves circulating
No.
around it? I mean, that could change the
It could. It could indeed. It could speed up.
Why do you limit yourself to binary information and not complete cluster information?
Yes. In a minute. You jump too fast. Okay. So if I have a binary, okay, and with a certain binary disk, what happens in this certain binary disk? You can calculate the torque, and whether it's retrograde or prograde, you can calculate the limit of this binary as it accretes gas, and its mass ratio gets more and more equalized, and mass increases. The binary separation gradually decreases. Eccentricity of the binary is limited, and one can do this kind of calculation. Or alternatively, you can do it with retrograde, and here you can also do it with Kozai. What about Kozai? All right, yes.
Was pumping up the eccentricity of the binary?
Yes. This is eccentricity of the binary relative to each other.
Well, what's pumping it up? Because it's in the gas disk.
Well, there is a torque from the central black hole. Okay.
Oh, okay.
So and then there is a binary of the two relative to each other. Okay. So Kozai, I hate to say that originally I thought it was very promising, and probably not. And the reason for that is in order for Kozai to operate, the apogee must be a significant fraction of the Roche radius, which means that you have to go, this is your work, John, and you have to go over with eccentricity 1 minus 10 to the minus 7, and to get there, and this is difficult to achieve. You have almost, and also Crystal, you've done some of this. You have to be very much perpendicular, close to perpendicular. But certain binary disk may play a good role, and if you have no gap formation, it would play a good role. Okay, but there's a more important role that I hate to say Simon has also anticipated already, and we're going to come to that. Okay. Now, so first of all, I want to go back to the galactic center. There's a lot of X-ray binaries here. And there is an overpopulation of X-ray binaries. Could they be formed? That's within 1 parsec. Could they be formed this way? Okay, one possibility that they could. And in fact, for many X-ray sources, I was told that the actual mechanism to produce powerful X-ray source has always been somewhat uncertain. And one possibility is that you can form a lot of these compact objects, and then they may accrete in the central regions to light things up. Now let's give you something more exciting to think about, is what if there are these binary black holes, and they are starting to keep on moving together because of this common envelope, or because of something else, which I'm going to talk about in a few minutes. And what if they start to get close enough and they start to radiate gravitational waves intensely, and you can probably produce some sort of gravitational wave source. And there are already two classic models, and one is a common envelope model, the other one is stellar cluster model, and both have their own problems. And how do you get such a massive black hole is one problem. And here, how do you stay inside the stellar cluster after all these exchanges is a problem. We can get around to this problem and this problem because our black holes, when it was first produced, it's just a few solar masses, but it accretes. It can increase its mass by an order of magnitude. It was born as a single, and then it acquires companions to give you this gravitational wave event. And and when they undergo any exchange, dynamical exchange, they are in the neighborhood of a massive black hole. They can never escape. Okay, so you can have these shortcomings you can overcome. And the idea here is we're trying to get just a few % market share, if that. Okay, so how do you do this? Now, Simon talks about the small cluster, and I mentioned that the isolation mass typically can contain several C black holes, and these C black holes can then interact with each other, okay, and they can start to form hierarchical systems, and they can undergo this kind of exchange mechanism that Heggie and Hudd and various other people have done over the years, except you're in an environment which is this environment that is bound in this region and interacts with the gas. And so even if you shoot something out of the cluster and they remain in this neighborhood and they get recaptured, okay? And simply because they're going around here at over 1,000 kilometers per second, and when they leave the little cluster, they're leaving at few % of the velocity, so they remain near here, and they get more and more compact, and you can have multiple systems and set up these type of multiple system and satisfy some sort of criteria, which is set up first by Voltanen, and you can get these kind of very compact objects. Okay, so that's one way to shrink their separation very quickly. I also mentioned about the spin vector, okay? In the very end, I talked about the disk being turbulent. Let's have a look. This is an AGN, typical simulation of an AGN disk. And this to here is 1 parsec. Here to here is 0.1 parsec. And here, the binary separation is less than 0.01 of a parsec. And eventually, you want to get down to a few 10 kilometers. So the binary separation is typically very small compared to the turbulent eddies in the background. So the eddy will give you different angular momentum. And you can have a guide here. There's a famous HK tau system where you see binaries with disk that is orthogonal to each other. And this type of situation is likely to happen here. And this disk will change in the background. And then you will have the circumbinary disk torque on the orbit of the binary. The orbit of the binary will torque on the orbit of the circumhole black hole disk. And the circum black hole disk will torque on the spin of the central star. And this will evolve on time scale of eddy turnover time. Okay, you can incorporate all of this with a Kolmogorov to first order, some sort of Kolmogorov type of approximation. You can consider all of these effects and then try to figure out what would be the orientation, the spin orientation, and spin magnitude of the individual black hole. And it turns out that spin magnitude could be relatively small, simply because the eddy turnover time scale is short compared to the accretion time scale. You would have changed the spin orientation many times, and they cancel out to give you a relatively small spin vector, but you can introduce a little bit of obliquity along the way. Whoops. So when we start to go into, get very close, and you can have gravitational radiation start to damp down the semi-major axis eccentricity, and then eventually this effect, the gravitational radiation effect, overcomes the torque that you feel from this circumbinary disk, and that occurs when the time scale, when this separation becomes small compared to this value. From that point on, the angular momentum evolution is essentially going its independent way, determined by the merging process. So that spin and obliquity is important because in principle we can measure that from the wave trains, from the gravitational wave events, and simply because the distortion of the gravitational field in the background is not spherically symmetric, and the radiation can give you a recoil, and you can work out from that recoil velocity, and this recoil velocity does depend on the angular momentum vector, and it depends also on the obliquity, and from that one can determine things like whether it can stay or it will go. If the spin angular momentum vector is small, and then they generally will stay.
How do you determine that recoil velocity?
There's a lot of people have done work in here, okay, and this is obliquity angle is related to that, and A1 and A2 are the normalized angular momentum vector, and so people had done these type of calculations when they look at binary black hole in numerical relativity, and to determine some kind, this is just an approximation. Okay, this was done by Madal and some others.
Did they do a whole bunch of simulations?
Yes,
Fit that thing?
you fit that.
Okay.
Okay. So you can get this kind of effect. If the black hole does not go, then the black hole can grow to intermediate mass, maybe 1,000 solar masses, and then it's like a Jupiter relative to a black hole, and being the sun in the center, and this Jupiter would excite spiral density wave and exchange angular momentum between the disk and that and that. But in the background, there is a nuclear cluster. So the interaction between this companion black hole and the nuclear cluster will give you dynamical friction. So you would undergo orbital decay, and that very process would remove angular momentum from here to here, here to here. Along the way, you clean up the disk. I will get to that a little later and to show you in the movie here. But that black hole also has an important influence. And there are some indication, and Simon would be very pleased, that there is, what is it called? Yes, that source. Seems to initially speculated by him to be an intermediate mass black hole. There is some indication to show you that the velocity here is high. It doesn't matter whether it's a black hole or not. The important thing is it's maybe relatively massive, comparable in mass ratio to the central black hole, comparable to Jupiter, to the sun. So this process could actually lead to secular perturbations, and it can change the orbit here. And one important question is, do they generate alignment of periapse in the same way as in the Kuiper belt objects? And there's another important effect. This is related to the sweeping secular resonance. So this object was once embedded in the disk, and the disk provided a little bit of gravity, and that gravity may have caused this companion to precess, and as the disk goes away, the precession frequency slows down, the resonance will move in. Now, why is this interesting? Because when we look at the S stars and the disk stars, and the stars are represented by these red arrows, you can measure their distance, you can measure their semi-major axis, and you will see that many of the disk stars have very large eccentricity. And these eccentricity are considerably larger than what you see if you use numerical simulation with either two-body relaxation or resonant relaxation. You can never excite them, the green dots. You cannot excite them to this value. But if you use sweeping secular resonance, and as the disk goes away, the secular resonance can move in, and this process can excite the eccentricity of many of these disk stars. So what happens when this black hole moves in, okay? And then, as I said, this black hole moves in because of dynamical friction, and it's going to drive the gas all the way in. This is one way to clear up the disk. Along the way, you may have resonant, mean motion resonant little black holes, and you can also have this process going in to give you clearing of the disk. I won't bother with that. And this may be, I'm going to finish in 1 second. So this may be the way to give you a duty cycle that the active phase can only last for 10 to the 8 years. Okay, so let me get very close to the end. Okay, and the next stage is you want to know is these intermediate black hole can almost be detected with advanced LIGO, and eventually we'll get there. So now let's consider the cosmological occurrence rate. You can integrate that, the trapping rate, you can integrate because you know the host stars, you know the redshift dependence, you can work out all of this using cosmological models, and this is very significant because today the horizon of LIGO is here, and when in a few months when advanced LIGO switch up, it will be there. So at this stage, within a few months, we expect one gravitational wave event every week. And you can start to do redshift distribution, spin distribution, mass distribution. You can integrate all of this together and see whether you can get a effect, and you can work out in terms of the dependence of mass-radius relationship and so on and so forth. And so this you can produce eventually as a probe to AGN structure. So let me give you the take-home cartoon. Okay, so I've talked about a process during the active phase of AGNs that the central massive black hole is surrounded by a gaseous disk, which will interact with certain nuclear clusters, and these clusters, some stars will be trapped. If they trap, they evolve into upper main sequence stars, and they provide pollutants to give you high metallicity, and they also produce single mass black holes. It's a bit like human story. When we were born, we weighed 4 kilograms, and by the time you're 30, you'll probably weighed 50 kilograms, so increase the mass of more than the order of magnitude. Most of us are born single. By the time we're 30, we have partners. So in many ways, and this is the story of these black holes, and then the black hole would interact with each other through various processes, certain binary common envelope disk, or these multiple star clusters. They interact, and you pack them, they interact, and they will merge, and they can produce, by my estimate, that is at least tens of % of the market share of gravitational wave events we see today. The most important prediction is that most of these events will happen with a relatively low spin, and also there could be events with mass that's in excess of what we have already seen. So if you can actually detect the possibility of over 100 solar mass black hole. I know there are people claiming that you can already rule that out based on 5 events. And, but I think we're in early days, and we will have a lot of surprises. And so this is the take-home message associated with the take-home cartoon. And the most important part of the message is that the AGN disk resembles protostellar disk and may trap nearby stars. Thank you.
So you rely on an intermediate mass black hole to drive up eccentricities of the...
It could. But there's only one. I mean, we only see it in the AGN here, right? We don't know whether the other clusters are with high eccentricity. But there's a problem to be solved in the disk stars. They have high eccentricity.
I agree. That's a problem.
Yeah.
Station times are way too long.
Right.
But wouldn't that also like have an impact on the S stars?
No, because once you're too far in, then the secular perturbation weakens. And in fact, in her calculation, she has already done that. In Xiaochen's simulations, these would be too far in, and the perturbation on them is too weak.
We can have the discussions upstairs, and let's thank Dahlia again.